Hello students, so we will continue this lecture on the potential step problem of the Schrodinger equation. And in the last lecture what we observed that for a particle whose energy is less than the potential step or the potential V naught, the situation is something like this, that the particle cannot cross the barrier. This is the classical result I explained you in the previous lecture. You can watch that I have it in the playlist. And classically the result is that if the particle energy is less than the potential height, it will stop at x equal to 0 and then it will bounce back or it will be reflected. This is the classical result. And classically there is no possibility of the particles or for a single particle with energy less than the potential to cross the potential step. It cannot cross. And I showed you via this diagram that it will come here and get reflected back. Quantum mechanically what we have to observe, quantum mechanically we have to solve the time independent Schrodinger equation and check the wave functions and the boundary conditions to find what physically is happening. And we had solved the equation and we got some equations like this. And what we observed that in the region x greater than 0, because this is the region which we are interested in, we have a wave function. We have a solution of the time independent Schrodinger equation, and this time independent Schrodinger equation shows that there will be a wave function in the x greater than 0 region which is exponentially decreasing. In the case of potential step, the x greater than 0 region, in the potential step is classically forbidden. Classically there cannot be any particle in this region, so it is classically forbidden. Classical mechanics says that if this is the region x equal to 0, this is x less than 0, particle has energy less than V naught, means this is V naught and this is the particle energy, then x greater than 0 is not reachable by the particle. Particle cannot go there. Classical mechanics has no option to enter the particle in this region, so this is a no entry region. X greater than 0 is no entry classically. But what we are interested in, observing the quantum mechanical results, and let us see what happens in the quantum mechanical situation. So we had some solutions, we had solved some steps, and we had reached to the conclusion that at x less than 0, as the particle is coming from the left hand side, in the x less than 0 the particle is moving, it is coming towards the potential step, it will be reflected back, and after that what happens in the x greater than 0 region, there is a exponentially decaying wave, and this is the exponentially decaying wave c e to the power minus e k to x. You can inject the time dependent part by writing the e to the power minus e omega t. However, we are interested in the probability density. So for x less than 0 it is a traveling wave, and x greater than 0 it is the transmitted wave, and it has no imaginary component, it is a real wave. So this part is very interesting. This part is very interesting, that it is a totally real quantity. Now to understand the physics, that what is going on, what we need to use, or the concept that we need is the probability current, concept of probability current. Now whenever we use the word current means it is showing some kind of flow. Net charge flowing per unit time is electric current. Similarly, you have water current, the rate of flow. So probability current is the rate of flow of the probability density in that particular region. How the probability density is flowing. If there is no flow of the probability density, then it means it is constant. If the probability density is 0, then it means there is no probability of finding the particle in that region. So this is somewhat similar to the flow of a liquid. You can see in this diagram over here, this is the liquid flow, this is the current. This is the current flow of water, and we are interested in observing the flow of current in this region, suppose. And this is the potential step. In the x less than 0, this is x equal to 0, this is V naught. Particle energy, suppose it is something like here, which is E less than V naught. This is x less than 0 and this is x greater than 0. Now these arrows, they denote the probability density, and here in the left hand side we have a traveling wave over here, and in the right hand side this wave decays exponentially. It is not 0. You should, I hope that, I don't hope, I am sure that you know the concept of or the speciality of the exponential functions, that they do not drop to 0 value instantaneously. It is a long process. It will touch the x-axis somewhere at infinity. So it is not that it will become 0 as soon as it crosses the potential step, and at x equal to 0 it is 0. It is decaying. It will be 0 somewhere far from x equal to 0. So the probability current has to be kept. So what is the formalism here? What is the method here? The method here is to calculate the probability density current, which is denoted by J, in this region x less than 0 and in x greater than 0. Now you must have heard about current density. Current density is also represented by J, current density, and it is a vector quantity J. So here also we are representing the probability density, probability current density, or sorry, the probability density current, or simply you can say probability current, by this quantity J. Now what the procedure is? Procedure is to find J. Procedure is to find or evaluate J in the regions of interest where we are solving the equation, in the regions of interest. This is what we have to do. Now let us see how we can do this. So the mathematical expression for probability density, I must have told you in the previous quantum mechanics lecture also. This is a quantity that is I h bar by 2m psi star del psi upon del x minus psi del psi star upon del x. Now the probability density you have to calculate in the region of interest, and our region of interest is x greater than 0. We will also calculate the value in the x less than 0. But for the time being, since our interest is in the x greater than 0, we will calculate this. Now see, the wave function in the x greater than 0 region is c e to the power minus k2x. It is a real quantity, so its conjugate will be same. Complex conjugate and the wave function, they will be same. So this wave, it represents the transmitted wave. Transmitted means wave on the right hand side, how the wave has crossed. So it is the transmitted wave. Now the probability current density for this wave function can be calculated by the equation that I told above. So the transmitted probability current density, you put the values of psi and psi star, they are same, and you find that transmitted probability, the probability density current for transmitted wave is 0. Now this is a paradoxical situation. This is a paradoxical, or you can say that it is somewhat confusing situation. The transmitted probability density is 0. What does this mean? Means that there will be no, transmitted means in the other side of the potential step, there will be no probability density. This is what does it mean? If this is the situation, this is x equal to 0, and here we have, this is the potential V naught, and suppose this one is the particle energy E naught. Here we have this exponentially decaying curve, and this is the transmitted wave. So the probability current density you can evaluate by keeping this wave function and its conjugate here. Since the conjugate and wave function are same, it will give 0. This means there is no current here. There is no flow per unit time. J transmitted is 0, means there is no flow of probability density in this region. No flow of probability density in this region. You must have seen these lectures in many videos and in the classroom. But there is a very interesting question here. The transmitted probability current density is 0. However, the wave function is not 0, and the transmitted probability current is 0 only because it is a real function. It has no imaginary part. It is not behaving like a wave. It is not something a wave like this. It is exponentially decaying quantity. This means if the particle has energy less than V naught, it will not be transmitted, and what will happen to this? It will be reflected, and this is the classical result. Classically it says the particle will come. This is the incoming particle or wave. This is V naught. This is the particle energy E, which is less than 0, and this is the reflected particle or wave. So there is no condition, there is no condition for transmittance. Now what will happen? We have to see this. So this is the situation here. We have a reflected particle or wave or incoming particle and its corresponding wave. Now in the this is the classical picture. The classical picture says that the wave or the particle will approach from the left hand side. It will come in contact with the potential step. Instantaneously or very small time it will stop and get back reflected back from the potential. So classically the x greater than 0 region is a no entry region. Here the particle cannot enter. This is classically predicted and it is correct. However, there is an interesting case, and we have seen here that the transmitted current density is 0. So this is in accordance with the classical theory. We can say that. However, the interesting situation is that when we calculate the probability density in the x equal to x greater than 0 using this wave function, this is somewhat like this. C square e to the power minus 2k2x. Now at x equal to 0, this p is maximum, probability density is maximum, and as x increases, it decreases exponentially. Means as you go away from the potential, as you are moving at larger distances from the potential, suppose this is the situation, this is x equal to 0, this is V naught, and as you are moving further in the positive x-axis, what happens? The probability of finding the particle goes on decreasing exponentially. The probability of finding the particle goes on decreasing exponentially. This is the interesting situation. Decreasing exponentially. The thing that we should notice, or that the thing that you should consider in this case that the probability density is not zero, means you have a probability of finding the particle in this region. And this is the difference from the classical case. Classical case says that at x greater than 0, there is the particle cannot go in the x greater than 0 if its energy is less than v naught. X greater than 0, positive x-axis is a classically forbidden no entry region. But in the quantum mechanical situation, you see that there is a finite probability density. Maybe it is decreasing exponentially as you are going further in the positive x-axis, but the probability density is not zero. So quantum mechanically, the particle can be found in the classically forbidden region. This is the significant result of quantum mechanics. Quantum mechanically, the particle cannot be, the quantum mechanically the particle has a finite probability, or write it in this way, that will be more convincing, or that will be more easy to understand. We should keep the language simple as possible. Quantum mechanically, there is a finite probability. There is a finite probability that the particle can be found in x greater than 0, which is classically forbidden, Classically, the region is forbidden, and quantum mechanically there is a finite probability that the particle will be found here. So, what is classically impossible, quantum mechanically it is possible. I have shown you the example in the case of Dirac delta function also, that if it cannot cross the potential step, it will just penetrate through. Although the penetration problem, barrier penetration problem, is a separate case, we will discuss it in the next lecture. Now, in the second part of this potential step lecture, we will consider the case when the particle has energy greater than V naught. Suppose this is V naught and this is the particle energy. Its energy is greater than V naught. So suppose there is a person who is running towards a barrier or towards a step, and his energy is quite high. So what will happen? He will cross this region. He will enter this region x greater than 0, means crossing the potential step. Maybe his speed will slow down. This is the effect of interaction with the potential. Some of the energy is lost. So now let us analyze this situation in quantum mechanical terms by solving the Schrödinger equation, and again we will make use of this concept of probability density current. Now for x less than 0, the particles are free and they have a repulsive potential at V naught, so that it stays for some time. Classically, the particles approach the step from left with constant momentum, and as the particles enter the x greater than equal to 0 region, where the potential is non-zero and equal to V naught, their momentum is reduced, their speed is reduced. So the picturization of the problem or the physical situation is the particles approach from x less than 0, then they cross the point Initially in E region, E less than V naught, they were not able to cross the point. They crossed the point x equal to 0. The momentum of the particles, or of the particle, if you are considering one particle, the momentum of the particle at x less than 0 is root under 2me. P is equal to root p square by 2m is E, and at x greater than equal to 0 it is root under 2m E minus V naught. E minus V naught. And remember that the condition is, you have to remember that we are considering the situation when E is greater than V naught. So this quantity is a positive quantity. Now let us see what happens, how to solve the Schrodinger equation and how can we get the solution. So the momentum is changing. However, I must tell you one thing, it is a word of caution, that the momentum will be conserved. It is reducing the down, it is slowing down, but it will remain conserved, because momentum conservation has to follow in every branch of physics. So the particles, they have sufficient energy. Classically, what will happen? This is the situation. Let me show you with a rough diagram. This is x equal to 0. This is E particle energy. Now the potential is somewhat like this. It is below this E. Particle is coming and it will be transmitted. So there is complete transmission as predicted by the classical theory, because the particle energy E is greater than V naught. Let me show you if I have a diagram. Right now I don't have, I will show you by a diagram. Classically the particles will be transmitted at x greater than 0, and or you can say as their energy is as E is greater than V naught. So it will be transmitted. This is the classical result. And it is quite logical also, that if you have energy more than the barrier, you can easily cross that. So there will be total transmission. The particles will come to the x greater than 0 region with their energy is less than that of x less than 0. The particle will have energy E minus V naught in x greater than 0 and E in x less than 0. So there is total transmission. Mind the word. Classically, what is predicted is total transmission. Means there is no chance of reflection. The particle will totally cross the barrier. There is no other option. There is no other possibility. Now let us see the quantum mechanical situation. So for quantum mechanical situation, what we have to do? We have to solve the Schrodinger equation. Quantum mechanically, the situation can be studied. The situation can be studied by the Schrodinger equation. So what does after solving the Schrodinger equation, I think at this stage you can write the Schrodinger equation for this situation. So I am not writing the complete equation. I am writing it in this form: d2 psi upon dx square plus you have this quantity k1 square psi is equal to 0. Then k1 is equal to root under 2m, will be root under 2me. So you are writing it in the two situations, plus and minus. So you have k1 is 2 root under 2me. This is for x less than 0, and in the x greater than 0, what you have? d2 psi upon dx square plus k2 square psi is equal to 0 and K2 is root under 2m E minus V naught by H bar. So this is the solution. This is the Schrodinger equation. This is equation number 2. This is equation number 1. Now as I have told you many times that K represents, what does it represent? It represents 1 by lambda. So it is the wavelength. You can see that the wavelength is different in two regions, x less than 0 and x greater than 0. This is the situation. This is x less than 0. This is x greater than 0. I have taken this diagram considering the complete solution, but this is the wave picture. The wavelength in x greater than 0 and less than 0, they are different. Why they are different? Because momentum is changing due to interaction with the potential. This you have to remember. So you can now write the solutions for the two regions. First solution is a e to the power I k1x plus b e to the power minus I k2x, x less than 0, and then you have psi 2x. So this will be different constant, so it is c e to the power I k2x plus d e to the power minus I k2x at x greater than 0. Now what will you do? Now the condition is that psi should be finite. Condition is psi x must tend to 0 as x tends to plus minus infinity. So in this region, if x tends to minus infinity, then the constant, then psi 1 x will blow up. So what we have to do? We have to eliminate some quantities. Which quantities we should eliminate? Now what happens here? This is the x less than 0, means this is the situation, x equal to 0, this is x less than 0, one wave is coming, then it is getting reflected back. This one represents the incident wave, a e to the power I k1x and b e to the power minus I k2x is the reflected wave. Now there is total transmission, so this is the transmitted wave, and this quantity is 0. Why this is 0? Because on the right there is no condition for reflection. D is 0 because at x greater than 0 there is no reflection. We don't know what is beyond x greater than 0. So we can take this condition that in the right hand side there is no reflected wave. So our wave function or solution is a e to the power ikx plus reflected wave b e to the power minus ikx in the x less than 0, and we have a transmitted wave e I k1, sorry it is k1, k2x in x greater than 0. This is our solution. Now how we can apply the probability density function, probability density current, and what is the difference between the classical and quantum result, we will see in the next lecture, because I have to take care of the time also. For the time being, please like, share and subscribe the videos, watch the videos and ask your queries if you have any. Please cooperate in growing together, learning together. Thank you.